my talk's going to be on the importance of label domain gaps. Like this is some work that like basically on an effect we observed within our machine learning team when working on different public perception tasks and working with a lot of different customers, but we saw the same thing happening over and over again, and we did some investigation to reproduce this. So today I just want to show you like what we found here. So as you can see here, all the nice faces from our machine learning team. I'm not going to go over all names, but yeah, you can see them here. So why do I want to talk about labels? You can see here two images that are just sampled from two different data sets. In this case, they're both synthetic, but that doesn't really matter in this case. It's more about looking at those labels. Do you think if you would combine those data sets for training, that you would improve performance over just using a single data set? In this case, like with its 10,000 samples per data set. And like, since I want to talk about labels, the answer has to be no, it won't help. Otherwise, I could stop right now. But you can see that there are quite some differences here. Some of them are subtle. Like the most obvious one would be the motorcyclist that you see here. It includes the bike, whereas this data set just annotates the rider. But there's way more different things here. Like on one data set, we have slightly larger labels, or like we annotate objects that are with way less visibility than the other ones. And this one actually, if you would merge these data sets, your average position in object detection would drop by 20% versus just training on one of those two data sets. So visually, you know, initially would think like that's fine, but it's actually not. So just to summarize quickly, like again, why I want to talk about these labels today is this alignment in labels is very critical when working with synthetic data, but also when working with real data. So you'll see the same effects when you just have two different real data sets that are labeled by different labeling providers, for example. Another thing like I want to highlight here is that many people think the advantage of synthetic data is that you have pixel perfect annotations, but actually when you mix them with real data, this is a problem and you need to address it. And yeah, these misalignments in the label specs, they're not super obvious all the time. And we've seen them a lot happening with, you know, when we just work on perception tasks and also with customers that we work with, and they're very easy to miss, but they make a huge impact on your training. So just a quick overview of how I want to structure this talk is first I want to give an overview of domain gap, since it's a very, I wouldn't say like well-defined, you know, term. So I want to give some more examples on what actually, how we observe, like view the domain gap and how we subsplit it. Then I just want to go into some common failure cases we see when mixing data sets. And then just show like how gaps in the label domain will confuse your models and actually make them worse. So when most people talk about domain gaps, you see like a synthetic image from our platform here and an image from Cityscapes. Mostly they just say the difference is in fidelity of the image, but there's actually way more to this. So if you would split this into an ontology, we could say like there's differences in the sensors, the optics, the environments that you use between data sets and the agents. So I just want to highlight a couple of these subgaps here. So just like going into the sensors, for example, in color distributions, you see an image here from Cityscapes again, and two images generated with our platform, but that have just different color distributions. When just you see like if you don't align these color distributions, you have a shift in this, which will cause a domain gap and cause problems for your model training. Another one would be a sensor noise or lens artifacts here, I think are quite nice, where you can see the same image just tweaked differently with the artifacts that you would see. Distortions that you would get from fisheye models on your cameras, and all of these obviously matter. There's also differences in optics and how well you tune your materials and lightings to actually match your actual physical values that you see, and in environments, which I think Lucas talked about before. How important it is to also match the domains of your data sets when you want to translate from day to night scenes or from suburban to urban scenarios. Another one I want to give a couple of examples on here is agents. So, the positioning of agents matters a lot. If you think about like where are all the areas bicyclists could appear, you can see in the image here, like there's one bicyclist riding in front of the vehicle, but that's likely not the only location where those will appear in the real world. So you want to figure out like, where do I need to place these agents to cover all the diversity that I would see in my target domain? And differences in texture, how closely can you match the geometries of your objects? At which densities do agents usually appear in your data sets? All of these things matter. But actually, in machine learning, we mostly do supervised training. So this all of this just focused on the input domain. So just how the images look like and how they're composed. But as I mentioned, in supervised training, we also have the whole label space. So actually the domain gap should consist here of like two subsplits. Like one would be the input domain with the examples I just mentioned. But there's also like label gaps in the label domain, which now I want to give a little more examples over. So one very common one is like just random errors that you would see in annotation. Like the contrast is the most clear when you compare it to synthetic data, because you don't have random errors in your synthetic data set. It's very rule-based in the way you extract these labels. So stuff like flipping classes randomly that you would get, as you can see on the bottom right here, where an annotator might, push the wrong button or not pay attention and wrongly label an object as person instead of cyclist. You wouldn't get this here. But it would also differ if you have different, labeling providers that have different levels of quality assurance. You have more or less amount of these kind of errors in these cases. Then, differences in geometry, how closely do you, how tightly do you annotate the boxes of your cyclists? Or what do you, consider false positives? So every now and then you will miss an object if you have humans annotated or like label an object that's not actually there. All these things that you usually don't get with synthetic data. Another gap is a gap in distribution. And here, for example, you have like gaps in class distributions and data sets. So you can see here just the pixel counts of different segmentation data sets. The blue one would be like a parallel domain data set, the GTA data set, and the cityscapes data set. You can see just by randomly generating data sets, you get quite different amounts of each class appearing. And those introduce a prior into your model during training, which quite heavily biases the model to predicting certain classes. Another one is the location. So just looking at the image space heat maps here, where do car classes usually appear in different data sets? So you can see here on the left is a heat map for new images. And we have two different data sets we generated with our system, where on the bottom right, you see a data set we generated where we forgot to spawn parked vehicles. And on the middle one, we spawn parked vehicles. The difference in detection was like almost 30% average position on cars by just forgetting to set this one value. So it makes quite a big difference here in tweaking those. Another one, if you think about regression tasks where you want to predict certain values, we also saw this, for example, here with optical flow, where we analyzed the histogram of the magnitudes of flow values on different data sets. So in the bottom left, you can see the KIDDI data set, which has flow magnitudes going 150 pixels of movement, 200 and up. Whereas like in the bottom right, we initially generated a data set that didn't have much values larger than 100 or barely any. So this one, combining it with the KIDDI data set, didn't help us in improving performance, but by just halving our hertz, like from recording at 10 hertz to 2 hertz, we would get a lot more high flow values, which then ended up halving our error on optical flow, and we would get way better on dynamic objects this way. But like those are all given, and like actually you could go way deeper on like random errors and distribution, but the main focus of my talk today is just around these gaps in label specifications. So I just want to give some more detailed examples here. So when I talk about label specification gaps or systematic errors, like if you have systematic errors that are severely enough, it's just like having two different, like a data set subspread split into two, labeled with two different label specifications. And what this would mean, like a different label specification, is if you look again here at the cityscapes data set, I'm not sure if you can see those trucks here, like both cases are labeled as trucks, so they're different size and shape. But as you can see on the right, we have a synthetic data set where we would also consider this object a truck, but this construction vehicle here, then the question is like, does this fall within the truck class or not? And you need to know like how you do this in your target domain, because otherwise you just teach your model different things between data sets. Other one would be, do you merge bicyclists and riders into one class, or do you keep them separate? And this one is a very difficult example, actually, where you see the curb class is part of the sidewalk unless it's around terrain. So you sometimes have classes that are mapped context dependent, and figuring this out is like, it's something you need to be aware of, and like sometimes hard even to match this, because you have to do a lot of search in your synthetic labels afterwards to find out, is this around a terrain or not? So just aligning those and picking a convention and sticking with it is quite important. So do you actually end up matching the curb to terrain, or do you just always keep it at sidewalk? There's also differences in geometry. So very common example here is, do you include the mirrors in the box annotations or not? Another one would be if you label 3D bounding boxes, especially if you want to do 3D bounding boxes from image detection and you annotate them in LiDAR space, you always have wrong calibrations between your images and your LiDARs, and you have a misalignment in time when the image is captured and the LiDAR is captured. So just projecting them back, usually what you see is like these boxes are slightly off. And if you have like a synthetic data set, usually you have them perfectly matching. So what you want to do, if you know that there's a systematic shift, you might just want to apply the shift to your synthetic labels to make sure that they line up. Similar thing happens if you, for example, annotate road boundaries. Usually, like it's quite common to just project images onto a 3D ground plane, a flat one, annotate it once and then project it back into all the images. But same problem again, depending on the quality of your calibration, when projecting back, you would actually not have the line be on the exact boundary, but have a slight shift. So same story again, like you might want to apply the same static shift to your synthetic labels here. Other examples on segmentation, it's quite a common one, is that on vegetation, we get labels that are very fine grained. You can see the little sky pixels through the tree, whereas if humans label it for time efficiency, you just draw blobs around it. So to match this, you might just want to dilate, erode your masks to make sure that you get similar effects here. For regression tasks, again, like you have sometimes humans labeling visibility values on your boxes, and usually they don't estimate float values, but you just bucket them into steps of 10 or 25. So if you get something out of our system, for example, you get floating point values, and you might want to line them up to actually round them to the multiples of 10. Otherwise, when training your model, you have a quite big shift in your values there. And last one, and probably the most important one, is what do you consider a true positive? So, is it just vehicles that participate in traffic? Are it only vehicles larger than 10 pixels or with more than 20% visibility? Like all these things you need to be aware of in order to, trim down your synthetic labels to match this. So you can see here the same image where we have a box around every object, and you can see here in the far distance there are a lot of small boxes of parked vehicles. Or you just do it like this here, where you only put boxes around vehicles that are more than 20% visible. So why do I talk about this is when you have synthetic data and real data, there are different ways how you could combine this. Like we already see some talks on unsupervised domain adaptation. You can see on the right, which I oversimplified with this little graph here. But assuming that you have a large amount of real labeled data, as we see it's the case a lot in the industry, you have two options of incorporating synthetic and real data. Either you go pre-training on your synthetic data and fine-tune on your real data, or you go the joint training route. And ideally, you want to be able to do joint training, because if you do pre-training, you have the whole problematic of catastrophic forgetting, and you might unlearn all the important features that you learned before. So now I want to focus on joint training and then just show what commonly goes wrong if you do this. So like this representation completely oversimplifies domain gaps. So let's assume we have a real data set and a synthetic data set, and we have some overlap in the input domain. So there's somewhat similar distributions. The images look somewhat similar, but there's still some distinction here. And we have in the label domain a clear gap. So let's say we have no overlap there. So this example would be the synthetic data set, we annotate the bikes and the riders separately. We also have boxes that are not visible in the data set, whereas in the other data set, you would see like they are merged and we only have boxes that are visible and larger than 20 pixels. Or in the segmentation use case, you would say like here we have simplified vegetation annotations and here we have fine detailed ones. So when we go about like just training on a public data set, like let's say with cityscapes, and just throw together the labels and train on it, we usually see something like this. So you see the pink line here would be the performance training only on cityscapes, and the green line would be jointly training on cityscapes and a similar sized synthetic data set, like in this case from our platform. And you see the model learns nothing from the added data, even though we doubled the amount of data here. And what we hypothesized actually is happening is the model learns to differentiate or classify the input domain in order to decide in which label specification to predict in. So initially what we thought what we have to do now is, okay, make sure the model can't differentiate anymore. So let's look at all the great work in domain adaptation and apply this here to make sure like these input domains overlap so heavily that the model can't differentiate anymore. So we did stuff like training GANs to make sure like the images look very similar, or apply discriminators in feature space to make sure that the model doesn't learn two different representations. The different papers on this, or use DAX to mix synthetic and real images, and just to avoid this effect. And the thing is, like, they work really well, and the model starts to confuse the input domains and just starts to randomly guess which label spec to predict in. And I can also see this here in the performance. Again, on the segmentation, we see like training only on real data here performs best. Joint training already performs slightly worse because the model wasn't able to differentiate the input domains. And then with each domain adaptation approach we added, we got worse and worse and worse because the model got worse and worse at differentiating the input domain. So where we usually see success is when you are aware of the gaps in your annotation specs and then just align them. So for some tasks, this is crazy easy. For say object detection on Kitty, you just merge the riders and the cyclists. You filter boxes that are not smaller than 10 pixels, less than 20% visibility, and then you can observe these performance gains that you get in bicyclists when mixing the data sets. So what we wanted to do next is actually validate that these hypotheses that we had is actually what's happening, that the model separates or learns to classify the input domains. And we did this by training only on synthetic data. So we generated two data sets and wanted to create an artificial gap on the input domain. How we did this is we had an image coming clean out of our platform. And then to add a gap in the input domain, we would add isotropic noise, Bayer noise, Gaussian blurring, and color shifts to the image to generate this more realistically sensor looking image that, it's just slightly different on this side. So we would have two training sets, one training set one would be with the clean images, and this one would get the noised images. And then we also needed to introduce a label gap artificially. So, okay. So we just took bounding box annotations in this case of all foreground objects. So it's the same foreground objects as you would see in cityscapes. So trucks, trams, bicyclists, cars, buses, and so on. And what we have on the left here is we kept the motorcycles and the cyclists separate. So it's just like the motorcyclist itself is annotated. We only keep boxes that are more than 20% visible and less than 80% truncated. So as you can see for the truck here. And in the label domain gap that we introduce, we then start filtering. For one, we start merging bikes and motorcyclists. You can see here, it now contains both. We dilate the boxes slightly by 3 pixels, something quite usually when you annotate data, you tell annotators to rather make the box slightly larger than cut off the object. So it's quite a common thing that you would see. And then we just change the way on what we consider a true positive. So instead of boxes that are less than more than 20% visible, we now say only if it's more than 30% visible and if it's more than less than 70% truncated. So what you can see is the truck on the left here would not be annotated anymore because it's too heavily truncated. These parked vehicles here on the right are filtered because they're too much occluded. So that's how we would generate our label domain gap. And what we did first then is train a model only on this training set 2, and then once by just throwing both data sets together. Oh, and yeah, and for validation, we just generated 2 validation sets that are actually the same images. And just once we kept images clean and took the label spec 1, and the other time we made them noisy and took the other label specs just so we can measure actually what's, on which data set it's performing better. So when training on this, you can see our baseline here. We also noticed that we weren't really aggressive with introducing label domain gaps here, so you still get a slight improvement here. But what's really interesting, if you look at this jointly trained network, so the gray one would be our baseline, just training set 2, and this one would be jointly trained on both. If you look at the predictions of this network, on the same image, so these are predictions from the same model, same image, just by adding noise to one and not noise to the other, you can see the model notices, okay, clean image means specification 1. I'm just going to put a box around the rider. As soon as I add noise, it's going to include the bike and also start filtering boxes over here. So it detected those cars before, but now it knows, so now I'm in label spec 2, I have to filter those. And you can imagine if you validate on you know, like this spec, you actually would get worse if you start predicting in the other spec. Yeah, so then just to mimic again what would happen if you now would do domain adaptation and like say, okay, my problem is my images don't look realistic enough or like don't match closely enough to my target domain. So we wanted to mimic this and just did the same thing here again, same data sets, but now we added noise to the training set one as well, but we still kept the label specs separate. So here again, it's just the motorcyclists, and here we would have motorcyclist and the bike included. And what you see now when you train on those is compared to just throwing the data together, you actually get worse. And you also get worse compared to your baseline. The reason is, if you look at the predictions again, what the model does now, it actually predicts boxes that are right in between these specs. So it's like right in the middle between where the foot of the rider would end and the bike would end. So it gets like, optimal scores on both. And can also see the objects that it would detect, like they're just the same, like it would still detect the truck over here and so on. So what would then happen if you just align your label domains and keep your input domains separate? So this one without noise, this with noise, but here we would have in both cases the bikes and the riders merged, dilated boxes and so on. You can see, okay, now we actually start to improve over our baseline and quite significantly. And you can also see this here in the predictions. Now it doesn't matter to the model anymore if the image looks noisy or if it's color shifted. It's just going to predict the same thing because we give it a consistent target on where to aim to. And this then enables the last use case of saying, okay, now let's align both, so labels and input domains. So we add noise to both, same label specs, and you can see, okay, now you can get an improvement over this. But up until this point where you took care of aligning your labels, there was no use at all at doing input domain adaptation. So like in our case, this would simulate perfect domain adaptation because we have like perfectly matching input specs. Up until we took care of the labels, every time spent on input domain adaptation is wasted time, basically. So now, if you see the prediction here, I think it's pretty interesting now. This model where input and label domains are aligned only has seen noisy images. So you can see actually the boxes get slightly less precise if you would predict on a clean image. So I think that's just something interesting. We want to investigate more if there may be even this benefit in having clean images in your training, because it's just like sort of an augmentation that you add to your training. Yeah, and like this also just doesn't hold true for bounding box detection, but also for segmentation. So you can see the same effect happening way more drastically. If you just align your input domains and not your label domains, your performance would drop like almost half compared to your baseline. And you can also see this very nice on the predictions again. So this is, again, just a model jointly trained without aligning your label space and having separate input spaces. The way we changed the labels here was that on vegetation, we made them blurry on one data set and made them precise on the other one. And you could see if we would feed this label domain one image, it would predict fine details on the vegetation. And if we would add noise to the image, it would start blurring them out, like making them blurry. Same for the pedestrians, for example. So yeah, the three takeaways basically I want you to have from this presentation is addressing those label domain gaps is a very manual process at the moment. So you need to understand, like, how are things labeled in my real data set, and how do I align this with the other data set do I have? Like, you likely run into the same problem as I mentioned before if you just have two data sets from different label providers, but especially with synthetic data where you have perfect labels, you really want to think about, like, how do I mess those labels up to look similar to my real labels? If you don't address your label domain gaps, input domain gap adaptation will just make your models worse. And having fine-grained control over the label generation process is very important to, being even able to addressing this problem. Yeah, thanks for your attention, and